right, chemistry students, we're going to get started with Chapter 10. There will most likely be 4 total videos of Chapter 10, and this first video is going to define acids and bases and actually go through really these first 3 objectives, reviewing those definitions, and then just really staring at what do they mean and looking at acid and conjugate base pairs. Okay, so that's where we're going. But before we get into the slides, I'm going to get out of the PowerPoint for a second. I posted a Chapter 10 PDF for you that lists some common acids, just listed out as their names and then the anion. That came from a different book. This table here from your book, you're really going to want to print this and have it in front of you. And I'm going to go ahead and say there are 6 strong acids. We'll define strong and weak in a little bit, but there are 6 strong acids, and there are these top 6 listed here with their appropriate formulas, and then 6 strong bases at the bottom. Your life will be a lot easier if you can go ahead and just memorize those 6 of each, okay? That's it, because any other one that you see is automatically going to be in the weak category because it's not one of the 6 strong either acids or 6 strong bases, okay? But you really want to have this in front of you so you can have the formulas familiarized and familiarize yourself with those formulas and start to be comfortable with recognizing an acid or a base. Okay, so there's 2 slides of objectives. You can go through them as the videos progress, but we're going to start by just defining acids and bases. So some of this is familiar. Remember, we had 2 definitions, the Arrhenius definition and the Bronsted-Lowry definition. I'm going to put a star by the Bronsted-Lowry because as you continue on into upper level chemistries and stuff, and you will see the Bronsted-Lowry more often, even though maybe in high school chemistry, if you took it, the Arrhenius may have been the only one that you actually went over. Okay, for acid, they're very similar. Okay, so for the Arrhenius definition, we release H plus in water. So if I have an acid HCl here, you think about it in water, it's aqueous, so all of these substances are aqueous, but it's producing H plus here on the product side and Cl negative, the anion, also on the product side. Okay, the base for the Arrhenius produces the hydroxide polyatomic ion OH negative. If you look at the Bronsted-Lowry, the acid is actually really similar. So you're thinking of a substance that donates a proton, whereas the base, this is where students maybe get confused because there's not an OH, okay? You're actually looking at a base accepts a proton. Remember, this H plus is a proton, okay? Sorry, I'm trying to underline that. It's not working, okay? So what you're going to see is acids reacting with bases. You're going to have reactions like that, or you're going to see a chemical reaction. You're going to say, oh, so this particular substance is acting as an acid because he starts with an H and he's going to donate it and give it away. So we are going to initially look at them individually. Here's an acid having removed, like up here, having removed the proton, donated it away. We don't care where it went initially. You don't care where it goes. You just know, okay, it's an acid because it donated a proton. Or we have a base all by himself, and then maybe later he says, okay, I'm going to receive a proton, so by definition he is a Bronsted-Lowry base because he's received a proton. On the right here are just a couple other examples showing there's the same HCl acid that we saw at the top of the slide, but in this case water is acting as a base and receiving a proton, okay? So we'll see these 2 reactions again, but I just wanted you to start to recognize that substances can act as acids and bases, and it's really just the transfer of an H plus or a proton, okay? I want to dwell on this H plus for just a moment here because we keep writing it as H plus like that or like that, but H plus in water, since all of this is occurring in an aqueous environment, it will react with water. In water, it forms this ion called the hydronium ion, which if you actually draw the Lewis dot structure is what this diagram is at the bottom of the slide, this whole diagram here. We have the Lewis dot structure of water, an individual proton, and then we have the hydronium ion, which is often H3O plus, okay? Remember, you have brackets here because it's polyatomic ion, and those brackets mean that this entire charge corresponds to everything in the brackets, okay? you will see the proton H plus and the hydronium ion H3O plus used interchangeably. If you want to, you can just stick with H plus. If you want to be lazy and not write the H3O plus, but you'll see them interchangeably. So when I talk about a proton being donated, sometimes the balanced reaction won't actually write the H plus, it will write the hydronium ion. So you need to recognize both. But as you're studying, if you just want to stick with H plus for the proton because it's simple, that is great, okay? This is an initial table of acids in your book that was gone over in Chapter 3. We actually looked at it in Chapter 5 when we reviewed Chapter 5. But it lists an acid, and then what it does is it shows, like, for example, this H is gone, and now we've lost that proton, that H plus, and now we're negative on the right. So it lists the acids on the left 2 columns, and then their corresponding anions on the right columns. Okay, so here was the hydrochloric acid we've already seen, and the Cl negative. You need to start to get familiar, and by the end of this video you should hopefully be really familiar with recognizing here's an acid who has not donated his proton, and now the proton is gone because we have a negative ion on the right. A lot of these ions on the right are polyatomic ions, like nitrate here, that you should already have memorized, okay? You should already know them. All right, so let's go back, keeping those definitions in mind. Let's go back through, what does that mean? So this is that same image from the definition slide, but when I say an acid, and I tell you an acid donates an H plus, you're thinking in your mind, this HCl has his proton attached to an ion, in this case chloride anion, and he's going to ionize out as H plus and Cl negative. This H plus is going to get donated to some base, donated, okay? We don't care where he's going right now. Right now, you're just recognizing that if I see a formula HCl, I know that that's an acid, and if he separates into the appropriate ions, I see the H plus proton and the Cl negative anion. So you should be familiar with recognizing that the proton here, just like a proton in the nucleus of cell, carries this positive charge because the substance on the far left has a neutral charge of 0, and now I've got a proton plus 1 and a chloride anion negative 1, which is totaling to a neutral charge, okay? We learned already that some acids are polyprotic, but I want to go over that. In other words, we have more than one proton. So you see the formula H2SO4, that's one of the strong acids you have to memorize, okay, one of the strong acids. You need to recognize that there are 2 protons that can be donated. So in the 2 reactions I have listed at the bottom of the slide, I'm showing the acidic protons in green, okay? So the 2 protons. First one comes off here, leaving me with HSO4, and check the negative charge there. All right, I only lost one positive 1 charge, okay? This guy is now kind of, look here, he's the reactant on the bottom reaction, and he now is an acid capable of also donating a proton, but that would be a weak acid, which is why we use the equilibrium arrow. Remember when we did strong electrolyte and weak electrolyte, if the arrow was a normal arrow like the top equation here, that's a strong electrolyte, in this case strong acid. And if we have equilibrium, that says weak. If we have an equilibrium arrow, then it's a weak acid, okay? That's why I say it will help you if you memorize the 6 strong acids and the 6 strong bases, okay? So let's look at bases here. Sodium hydroxide is probably the most famous strong base that exists. If you do a lab with a base, most likely it's sodium hydroxide, okay? So this is the Arrhenius definition, forming OH negative in solution right there. Solid, we mix it in water, and now we form an OH negative in solution. Calcium hydroxide, which recognize that that formula there has the parentheses around the hydroxide ion, okay, forms a hydroxide ion also, okay? So these are completely ionized. We form a Ca2 plus and a sodium 1 plus, okay? Pretty straightforward. Weak bases, you're going to also see the equilibrium arrow. So NH3, you should recognize as a weak base. You're going to see NH3 is probably the most common base in your world in chemistry, okay? So NH3 is really, really important. for you to keep an eye on and recognize that it is a base, because it is really hard to look at that and say it's a base when your only knowledge might be from, for example, calcium hydroxide or sodium hydroxide. Okay? You should be familiar, though, with the NH4 plus ammonium polyatomic ion. Okay? So this chemical reaction on the bottom is just demonstrating that NH3 is a weak base, and we have the equilibrium arrow. But if that is confusing you, just start with, remember, the Bronsted-Lowry definition is just that we are accepting a proton. So let's just focus in on the base accepting a proton. Okay? We can even balance it, plus a proton that he is accepting. And now he forms NH4 plus, the ammonium ion. So he had 3 hydrogens on the left, he's got 4 on the right. That follows the Bronsted-Lowry definition of a base. Do you recognize that we have a neutral charge on the left, and now we added a proton, which is +1, so therefore we have the +1 charge. So our charges balance, okay? Let's go back to acids, okay? So there's, you've got bases in your brain. Let's go back to acids. I want you to, once again, you really need to recognize what an acid is when you see the formula. This is that same HCl that we've been looking at. It's just the Lewis dot structure reacting with water, okay? Reacting with water, you should already know HCl. What does that break up into? You've already seen. It breaks up into H plus and Cl minus. I'm writing the H plus down there because what does this equation use? The hydronium ion, okay? And the hydronium ion actually allows the equation to look more balanced, okay? So it looks more balanced with the hydronium ion than if you were to just write H plus, okay? But in this case, look at the formula more clearly, whether you like the Lewis dot structure or the one that I wrote, okay? HCl is acting as your acid, and note its appropriate negative anion partner on the far right, the chloride anion. Water is acting as a base. H2O alone has received a proton, and he is now H3O plus. Okay? Start to see that pattern and recognize that pattern. One of the things I also want you to recognize is what I'm going to call the acidic proton. Okay? So whether you see the formula as HCl for this substance here, okay, or you see it as, for example, HNO3, nitric acid, one of the important acids you need to know, recognize that this proton can easily leave, leaving you with NO3 negative, okay? And this is the acid you already saw, H2SO4, a few slides ago that had the oranges on it, that slide, okay? This H3PO4, okay, is also a polyprotic acid, okay? So these are just showing the Lewis dot structures without all the little lone pairs that are showing common acids, and I just want you to be able to recognize, looking at the Lewis dot structure, I can see this H plus can leave, I can see this guy can leave, okay? He is an acidic proton that can be donated away, okay? So there's some shorthand that you're going to see that'll help you as you're practicing these before you start recognizing all of the acids and bases, okay? You can abbreviate an acid HA, and then the anion that corresponds once the proton's been donated as A minus, okay? You'll see that abbreviation for acids. Bases can be a little bit difficult, but we often start with just plain B, and he is sometimes generated with the little lone pair next to him. When he gains his proton and he accepts his proton, he is now BH with a positive charge. Now I will make a note, this equation at the very bottom of the slide here starts with a negative B, and therefore the final product is just BH, neutral, okay? That is totally an option. It just depends on what the base is. So this top equation follows the B that I wrote up here, and the BH plus is a product. And then the bottom equation, it's kind of like B negative, and now he forms just BH neutral, okay? So start to recognize these are pairs, whether the pair is HA and A negative, B with BH plus, B negative with BH. They are all pairs, and we just need to recognize, okay, HA starts with an H. He donated the H away, proton, leaving me with an A negative. So put it together in a formula. Just follow the reaction at the top, we have a base reacting with an acid. So you don't need to pay attention to this blue arrow that looks like a little reaction arrow, okay? But if you notice, he's kind of stealing the H that the acid is going to donate. That's what that arrow is just trying to show, is he's stealing that H. So our product is the base that has received the proton and the A negative that donated the proton away, okay? So this reaction, even if the arrow scares you a little bit, you can just kind of ignore it for a minute. That reaction should not be too scary, and keep in mind it's got the equilibrium arrow if it's a weak system, and it's reversible going backwards and forwards, okay? All right, so hopefully now that you've kind of got an idea of acids and bases, I want to make something clear. Certain substances are amphoteric, which means they can act as an acid or a base. And the best example of this is water. So in this upper reaction here, okay, water is acting as a base. So follow, we've got our same HCl acid that we've already seen, hydrochloric acid. Water is accepting a proton from HCl and becoming H3O positive, so water is acting as a base. The lower reaction, water being amphoteric, is reacting with this base, and now he's the acid. You see how I'm sort of starting to label the substances? I already told you needed to recognize this NH3 as a base, okay? So now water is acting as an acid, and he has lost his proton, he becomes OH negative, so there's his partner of A minus, okay? And NH4 base gained a proton, and he's NH4 positive, okay, ammonium. All right, so recognize those partners. We're going to give those partners a name. They're going to be called conjugate acid-base pairs, okay? So here's a new acid. We've been dealing with HCl. Let's look at HF now. When he donates his H plus, that's what's going on, we have an F minus. So this guy here is the acid, okay? F minus is a conjugate, and you need to know this name, conjugate. I know this is going to throw you for a loop. This guy on the right, F minus, is called the conjugate base. He is the conjugate base of that corresponding acid, okay? So draw a little line. Another example. H2O on the left is a base, okay? He has gained a proton, becoming H3O plus. This is the conjugate. If you see a pattern from what was on the top example, this is now going to be called the conjugate acid of the H2O base, okay? So you may be given an acid and asked what is the appropriate conjugate base. So you are going to remove a proton and make sure that the charge now loses one positive one charge. In this case, now that it has lost it, we go from 0 to -1. Or if you're asked, here's a base, what is its conjugate acid? You need to gain a proton as well as a corresponding positive charge. So base B, BH plus. That's all you do, okay? So you just kind of have the opposite names. So I'm going to go through this next example. So I am telling you each of these is a base, okay? And the question is, write the formula for the conjugate acid, okay? So each of these is going to receive a proton. It's going to receive a proton. Now, in the first one, that's very similar to what we just did and what we just saw. So hopefully receiving a proton, H3O. We have 2 initially hydrogens, so now we're going to make it 3, and we change it to a positive 1 charge because this is a 0 charge on the left, water, okay? Now, oftentimes, you can just write the H and then the rest of the substance. If there's no H, for example, like this third one. And so if you're not sure, you might just want to start by saying, okay, H and then NH3. Oh, I've already got H. Let's not write it that way. Write it like NH4, and I've got to gain my positive charge because it started neutral. Now it's gaining proton, positive 1 charge. Carbonate, polyatomic ion. Write your H first. Now, the charge is where you're like, it starts as -2. So -2 plus a positive 1 is going to give me a -1 charge. So the whole charge on that is going to be -1. Okay? The last example already has an H, so instead of an H2, I'm going to make it an H3, PO4. He starts as -1, so he's just going to be neutral, okay? I'm going to erase because I animated in these so you can see, okay, the appropriate answers. So you should be able to go backwards and forwards. If I gave all these as acids, you could donate the proton and write the appropriate new conjugate base for the acid, okay? What you're thinking of, though, when you're doing each of these is like this image from your book. These are all acids on the left. They've donated their proton. That's this H+, H+, H+. And then what's in blue are the corresponding conjugate bases. So that's what's going on in the background in your mind. So these are both, the last slide and this slide, individual examples of here's a base, what's its conjugate acid, or in this case, this slide, here's an acid, what's its conjugate base, okay? What we're going to next do is put them together in a chemical reaction so that you can label all 4 parties, the acid, the base, the conjugate acid, and the conjugate base, okay? So your book has an image, except it just labels it base, acid, okay? It doesn't actually put the word conjugate in there, all right? So here's your base, here's your acid, okay? And if you want to just make a note, the acid is paired in these black lines below with its corresponding. So I would put a little conjugate up here to make it clear. That's the conjugate base. A negative is the conjugate base of the acid HA, and this on the far right is the conjugate acid of this corresponding blue base on the reactant side. Okay, so this is putting together what we saw on the previous slides for individual substances, but now we're within an equilibrium reaction with an acid and a base reacting. Okay, let's look at several more examples. So the next couple slides are just some more examples, okay, and I just want to be super clear. The original base becomes a conjugate acid. The original acid is now called a conjugate base. So this here is the generic form, the generic format for what I already showed you on the previous slide, okay? And here's just a real example. Water's acting as a base. This HCHO2 is our acid, okay? So we lose that proton and become a negative charge. So the green guys are paired together as an acid conjugate base pair, and the blue guys are paired together as a base with his corresponding conjugate acid. Okay? So you need to start recognizing that. Recognize the pairs, in this case they're color coordinated green and blue, and recognize who is acting as what. If you were to look at this entire reaction at the very, very bottom, could you identify that it is an acid reacting with a base? All Bronsted-Lowry definitions, all just a transfer of a proton, not a lot of super complex chemistry, okay? So the products are a lot easier to write than some of the other stuff we've seen this semester, okay? So let's look at some more examples. NH3 is a base, we've already gone over that, and in this case water is an acid, okay? So NH3 is the base, water's the acid. And you could recognize that if you actually just said, all right, where is this substance on the product side? Oh, let me look for a nitrogen. All right, here's a nitrogen. He's gained a hydrogen, and therefore this guy must be a base, and this guy is his corresponding conjugate acid. By process of elimination on the reactant side, the other substance is an acid. And we've already discussed that water can be an acid or a base, okay? So let me erase that so you can look at it more clearly. All right, so the acid donates his proton, becomes the hydroxide negative, which is his conjugate base, okay? If you don't like this image at the top that doesn't show everything, you might like this one at the bottom that's a little bit more colorful and is trying to show acid conjugate base, and there's actually like sort of arrows going on. If that helps you, you can zoom in on that and recognize the image on the bottom, water's acting as a base, and HF is your corresponding acid. Okay, so that's HF reacting with water. You have to look at the products to recognize who is the acid and who is the base. Okay, so now that you've got that in your brain, go back to, we're going to look at acid strength next. Just a little bit of acid strength. We're going to do more on acid strength in the next video, okay? But I want you to start, go back to this image, and I really want you to start memorizing just the formulas of the 6 strong acids and the 6 strong bases. And do you see a pattern? Okay, now we have one of the strong acids and his corresponding conjugate base. These arrows here show increasing acid strength, okay? So your perchloric acid is the strongest acid on the 6 strong ones that you need to memorize. Sulfuric acid is the second strongest. And do you see that the corresponding base strength is kind of the opposite here? So if I have a really strong acid, recognize that the conjugate base is a weak base. Look at water. Water is not a strong acid, but he produces OH minus, which is a strong base, okay? So just pay attention to that pattern. I don't want you to just stare at this and be like, whoa, there's way too much to memorize, okay? Look at the pattern and know the 6 strong ones in your life will be easier as you're assessing the pairs. So keeping that in mind, just a couple more examples here, okay? If I have HA as a strong acid, what that means is he easily breaks up into H plus A minus, okay? Remember that big arrow. Strong means forward arrow, all right? If this guy is strong, read the blue text, then this is a weak base, okay? Because it doesn't really like its proton. He wants to just kind of stay as A negative, okay? Whereas if HA is weak, then A minus is a strong base. And that was the like water is weak and OH minus is a strong base. All right, and you can think of the equilibrium arrow leaning to the left on the bottom one or leaning to the right on the top example, okay? This is a generic example. Stronger acid is going to produce a weaker base, whereas a stronger base is going to produce a weaker acid. And these, they just don't write from the image from your book, they don't write conjugate there, okay? They just don't write the conjugate pairs. I like writing the conjugate because it's very clear where we are in the reaction. So here's a real example. I've got a weaker acid, so acetic acid is not one of the 6 to memorize, so by default you should know he's one of the weaker ones, okay? I already told you water's weak, okay? So the weaker acid here, this base holds this proton less tightly. Ultimately, we're producing a stronger acid on the product side because this base holds his proton less tightly than this. This guy is a base. Remember, he's the conjugate base. The acetate ion is the conjugate base of the acetic acid on the reactant side, okay? So if you go through that, that is helping you assess. You got to know the pairs to begin with, but that is helping you assess strength of acid. We'll get more into strength in the next video, and I know this was pretty long, so thank you for listening, but I really wanted to give you lots and lots of different examples. Okay, so thank you.